Hello, this is my video lab report for Lab 3. In this lab, we're going to analyze the motion of a star to find the net force acting on it at all points, and we're going to apply Newton's law of gravitational force to estimate the mass of a black hole. Newton's law of gravitational force states that any particle of matter in the universe attracts any other particle with a force directly proportional to the product of their masses and inversely proportional to the square of the distance between them. One might ask, why are we doing this? Analyzing the motion of a star and estimating the mass of a black hole provides some information and insights that are helpful for further studies in relevant areas. Our system in this scenario is the star that is rotating around the black hole. We're focusing on it to analyze its motion and find the net force acting on it at every data point. For this animation, the initial value of time was set to 0 and the initial position was set to be at this point. In our calculation of the net force, we make two assumptions. Number one, we assume that the time between data points is 1 day. Number two, we assume that the net force on the star is due solely to a black hole. At each data point on the star's trajectory, we do the following. First, we record the initial and final velocity. Then, we use the momentum equation to find the initial and final momentum. Using the results, we calculate the change in momentum, which we divide by the change in time to find the net force. The value for the change in time is said to be the equivalent of 1 day in seconds. This animation shows how the magnitude and direction of the net force changes along the star's trajectory. And right here, we can see how the magnitude of the net force changes with respect to the star's distance from the black hole. As a reminder, Newton's law of gravitational force tells us that the net force acting on the star is inversely proportional to the square of the distance. This relationship is represented in the graph we see here. As the star moves away from the black hole, the net force decreases. And as the star moves closer to the black hole, the net force increases. To find a formula for calculating the mass of the black hole, a derivation can be made from Newton's law of gravitational force. Implementing the derived formula in the code gives us an estimation of the mass of the black hole equal to 4.34769 times 10 to the power of 34 kilograms. From the momentum principle, we know that the net force is equal to the derivative of momentum, which means that the net force is the instantaneous rate of change of momentum. This indicates that the rate of change of momentum gets closer and closer to the net force as the time interval gets closer and closer to 0. This is also true for the parallel and perpendicular components of the net force and the rate of change of momentum. As we saw earlier in the calculation of the net force, the time interval was chosen to be 1 day, which is not close to 0. This constitutes one possible source of discrepancy in the calculation. Let's suppose that the black hole was replaced by another black hole while the motion of the star remains unchanged. Is it possible to tell the difference? The answer is no. However, we would be able to tell the difference if the trajectory of the star changes, because that means that the black hole acts on the star with a different force at each point, indicating a different mass. In conclusion, the elliptical trajectory of the star is caused by the relationship between the net force acting on the star due to the black hole and the distance between the black hole and the star, which is demonstrated by Newton's law of gravitational force.